In a previous video, we had talked about basic equations that are relevant for compressible flow. So we're going to continue the introduction to compressible flow, and the goal in this short video is to come up with an expression for the sound speed. So in the case of incompressible flow, let's back up a bit. In the case of incompressible flow, let's look at the equations counts we have, right? So in this case, rho is a constant. So what we would need is conservation of mass. That gives me one equation. We would have Newton's second law in each of the three coordinate directions. So that gives me three equations. And let's look at all the unknowns in our problem, right? So the unknowns will be the three velocity components, u, v, and w along the three coordinate directions, and also pressure. So we have a total of 4 unknowns. And keep in mind, density is a constant, and it's a known constant, right? And likewise, we also know mu is also known. And so we have a closed system of equations in the sense the number of equations, the number of unknowns match, right? And this is how it does in the case of incompressible flow. Let's think about compressible flow. How are things different in the case of compressible flow, right? First of all, density is not a constant, and the density and temperature are related through an equation of state, which we have talked about. All right, and so P, rho, T are related via a state equation. And so let's look at the equations that we have, right? So we have a conservation of mass equation, which will be the the compressible version of conservation of mass equation. So that's one equation. We have Newton's second law. That gives us 3 equations for the 3 velocity components u, v, and w. Then we have a conservation of energy equation, which would be one more equation. And then finally, we have an equation of state, which is one more equation, right? So the total number of equations we have here is 6, all right? And the unknowns in compressible flow would again be u, v, and w, the 3 velocity components, pressure, density would be an unknown now, and finally temperature. All right, so temperature we typically obtain through the conservation of energy equation. So the number of equations and the number of unknowns match, right? So that's the difference in how incompressible and compressible flows may be analyzed, and hopefully that message is clear at this point. All right. Now, from a previous video, we also found for an ideal gas, we had the following result: TdS, ds being the change in entropy, is dH minus V dP, V being the specific volume, which is simply by definition 1 over the density. All right, and then we integrate this equation, S2 minus S1. The result we got was, in the case of an ideal gas, Cp ln T2 over T1 minus R, the gas constant, ln P2 over P1, right? So this is the result from a previous video. And if you assume the flow is isentropic, right? So if you assume the flow is isentropic, so the word isentropic means there's no change in entropy. So in other words, S2 would be equal to S1. So if we did that, clearly Cp ln of T2 over T1, and I can raise this to the power Cp. That gives me this term right here. And this would have to be equal to the ln of P2 over P1 raised to the power R. All right, so I get that by setting this expression to be 0. Okay, I can rearrange this and write down T2 over T1 is simply to the power Cp is simply P2 over P1 to the power R, right? So from here I can solve for P2 over P1. I move that to the left hand side. P2 over P1 is simply going to be T2 over T1 to the power Cp divided by R, all right? And I can write this as T2 over T1 to the power of Cp, and R, if you recall, is simply Cp minus Cv, the difference between the specific heats. All right, and the reason I'm doing this is now I can use the relationship between Cp, Cv, and gamma, and if you did that, P2 over P1 would be equal to T2 over T1, and I can take the numerator here and the denominator here and divide by CP. So that'll be 1 over 1 minus, and here I would get a CV divided by CP, which is simply the inverse of CP over CV. So that's 1 over gamma. All right. So in other words, P2 over P1 would be equal to T2 over T1 to the power of gamma over gamma minus 1. So what this expression really tells us is if I have two states of an ideal gas, states 1 and state 2, and if I'm going from state 1 to state 2 through an isentropic process, because remember there's no change in entropy, then the pressure temperature are connected by this expression. Also, if you recall, again from an earlier video, we got this S2 minus S1 is equal to CV ln T2 over T1 plus R ln rho 1 over rho 2. All right, you can go through the similar argument as I laid out to get equation 1. And so in the case of an isentropic problem where S2 minus S1 equals 0, so this would be the situation of the flow where isentropic. I can work out that T2 over T1 to the power of CV would be equal to rho 1 over rho 2 to the power of negative R in this case, right? So in other words, I'm going to set this expression equal to 0, rearrange the left hand side and right hand side, and remove the ln term over here. Okay, so I can write down T2 over T1. I can solve for that is simply rho 2 over rho 1 to the power gamma minus 1. That's easy to work out. So we'll label this as equation 2. And then finally, I can combine 2 in 1. I can substitute 2 in equation 1. And what we end up getting is P2 over P1 equals T2 over T1 to the gamma over gamma minus 1 is also equal to rho 2 over rho 1 to the power gamma. All right, so we'll label this as equation 3. All right, so these temperature, pressure, density relationships for isentropic flow are very important. All right, in the next part of this video, we will look at an expression. Our goal is to get an expression for the speed of sound. All right, and we can think of the sound wave as simply a perturbation. And let's say upstream of the sound waves, the pressure, density, speed of sound, temperature, or P, rho, C, and T respectively. And downstream of the sound wave, let's say the sound wave goes by, there's a perturbation, so P becomes P plus dP, density becomes rho plus d rho, speed of sound might change, C plus dC, and then the temperature might become T plus dT. All right, so I can imagine a control volume around this one-dimensional sound wave, if you will, and we know how to do control volume analysis for one-dimensional problem. And we can make the this a stationary wave, so the fluid is actually coming in on the left side and then leaving on the right side. Okay, so we are in a reference frame. We can think of this as attached to the wave itself, which is moving at the speed c. Right. So if you apply conservation of mass, all right, coming from the left side, we have density, and we imagine a unit cross-sectional area perpendicular to our sketch. So it's rho AV, so it's simply rho times C is the speed of sound, and A is simply 1, equals rho plus d rho times C plus dC, right? I can expand the right-hand side. I got rho C plus rho dC plus C d rho plus finally d rho dC, right? So I can knock off the rho c's on either side of this expression, and then I'm also going to neglect, I'm going to think of this as a higher order term, so I'm going to use the notation HOT for higher order terms, because this is the product of two differential quantities, d rho and dC, right? So that's sufficiently small actually in the limit that actually goes to 0 relative to the other terms that are remaining, and so that's perfectly all right to make that observation. So we are left with rho dC equals minus C d rho. In other words, C, the speed of sound, is negative rho dC divided by d rho. Let's label this as equation 1. Just like we apply conservation of mass, we can also apply Newton's second law. So let's apply Newton's second law. So we can remember it's got to have rho AV times V or rho AV squared term. So in the downstream side, it's going to be rho plus d rho times C plus dC squared, and the area is simply 1, minus on the upstream side is simply rho AV, so it's rho C times 1 times another C, and you understand where these things come from our one-dimensional analysis. In the flow direction is P minus P plus dP, right? So there's the difference in pressure, has to be multiplied by the area. So there's a unit area multiplying all of these terms, which we have taken out. All right, so let's think about expanding the left-hand side. So left-hand side is simply going to be rho plus d rho multiplying C plus dC squared is going to give me C squared plus dC squared plus 2C dC minus rho C squared equals, and of course here the p's cancel out, and I'm left with negative dP. Let's expand this further. So I'm going to get rho C squared plus rho dC, that's dC squared, plus 2 rho C dC, plus I take this d rho term and multiply that throughout my expression. For some reason, I seem to be losing the screen. My apologies. All right, so then I have to take this d rho term and then multiply each term over here by d rho, and I'm going to accumulate all of them. So the first one is going to be plus C squared d rho plus d rho dC dC plus 2C dC d rho minus rho C squared equals negative dP, right? So this rho C squares are going to cancel out, and let's see what we're left with. These terms which have a DC product of two differential terms, we think of those as HOTs or higher order terms, HOT. Likewise over here we have a triple product, we have this double product, so we can neglect those higher order terms, and if we did that, what we're left with is 2 rho C dC, this should be a dC right here, plus C squared d rho equals negative dP. Okay, and so I can solve for dC as negative dP minus C squared d rho divided by 2 rho C. So label this as equation 2. And then if I substitute equation 2 in equation 1, substitute 2 in equation 1, which we obtained above, I'm going to get C equals, I'll make that a plus, rho, and then it's dC divided by d rho, but we now have an expression for dC is dP plus C squared d rho. Remember the negative sign is, the two negatives make it a plus, divided by 2 rho C d rho. Okay, the rows cancel out, and what I'm left with is C squared equals 1/2 dP over d rho plus C squared over 2. I can rearrange this and obtain dP over d rho equals C squared. So this is equation 3. Just a historical note, it turns out Isaac Newton had assumed, starting with an ideal gas equation, P equals rho RT, he had assumed that the sound wave is essentially an isothermal process, right? So if you assume if it's isothermal, that means temperatures are constant, and so from here I can actually obtain an expression for dP over d rho, and dP over d rho is simply R times T. So according to Newton's approach or Newton's assumption, C squared, the speed of sound, from equation 3 is simply RT, and which means C is equal to square root of RT. It turns out this result is gives me the speed of sound in air, which is actually about 20% lower. for the speed of sound in air, right? So something is amiss with regards to this assumption. It turns out the right assumption to make is actually it's an adiabatic reversible process, or actually it's an isentropic process, right? So the correct assumption to make is the sound propagation through a medium is essentially an isentropic process, in which case we know that the c squared is dp d rho. Now I can write dp d rho as the partial of p with respect to rho at constant s, right? Because it's an isentropic process. And with the equations that we have for ideal gas, p over rho raised to gamma is a constant, or p over t raised to gamma over gamma minus 1 is a constant. These are results for isentropic problem. And also combining that with p equals rho RT, it's actually easy enough to show that the partial of p with respect to rho, it would simply turn out to be gamma rho to the gamma minus 1 times a constant. So I can write this as gamma rho to the gamma minus 1, and that constant is essentially what I've got over here is p over rho raised to gamma. So this is simply gamma p over rho, and gamma p over rho, I can write that as simply gamma RT. All right, so c squared equals gamma RT. In other words, the correct speed of sound is square root of gamma RT, and gamma has a value of about 1.4, and that actually explains that 20% difference that was mentioned earlier.